Welcome to physics class on alternating current, chapter number 7 of CBSE class 12. Now let's try to see what are the points to be discussed in today's video. Okay, there are many topics to be discussed, but out of these many topics that need to be discussed in alternating current, for the first video I will try to make for the first three topics, that is alternating EMF and current, second average or mean value of alternating EMF and current, and the last will be root mean square value of alternating EMF and current. So the remaining portions of the topics to be discussed under this alternating current, I will try to make it by parts. Okay, in the next video it may be of the number 4, 5 and 6. Likewise in the next again third video it will be of 7, 8, 9. Okay, likewise it may be coming in some parts for the remaining topics. So now for today let's try to do about this alternating EMF and current. Now this alternating EMF, what is this alternating EMF and what is alternating current? Let's try to know it this first. So your alternating current is nothing but it is that current which continuously changes in magnitude, okay, and periodically reverses its direction. That means you can also say like this: alternating EMF is that EMF which continuously varies its magnitude and periodically reverses its direction. That type of EMF we call it as alternating EMF. And similarly, alternating current is that current which continuously changes or varies its magnitude and periodically reverses its direction. Now how can we represent this alternating EMF or alternating current? Alternating current and alternating EMF, as per definition, its magnitude will continuously be changes and reverses its direction periodically. That means after a definite interval of time, the direction of the either EMF or either this AC current will have to reverse its direction. So that this, by knowing this property, that means magnitude varies continuously and changes its direction after a definite interval of time, then what happens? It can be fulfilled by the sinusoidal functions. So sinusoidal function, either you can take it as sine function, trigonometric sine function I mean, or a cosine function. So let's take it first for the sine function, how it can have these properties of changing magnitude continuously and reverses its directions periodically. Let's see. Now E is equal to E naught sine omega t. This is the equation for instantaneous sinusoidal EMF of the AC current, and this is the alternating current. I is equal to I naught sine omega t, where E naught and I naught are the maximum or peak value of AC EMF and AC current respectively, where omega is nothing but this is the angular velocity of that AC current, and t is that time at that instant we take it the instantaneous EMF and instantaneous current. Now let's try to have a graph just to show that the sinusoidal functions of EMF and the AC current. Now x-axis, along this x-axis we need to draw either what theta, that means the angle which is equal to omega t, or you can make it in terms of time also. And along y-axis let's try to draw either instantaneous EMF or instantaneous current. So in either it may be instantaneous EMF or instantaneous AC current. So instantaneous EMF will be drawn with a blue color and instantaneous current will be drawn with a green color. So what happened when E, okay, is equal to E naught sine omega t, then what happened if you take it that at time t is equal to 0, omega t will be equal to 0. So sine 0, we know that sine 0 is equal to 0, so your E will be equal to what? 0. When t is equal to 0, that means at the origin, what happened, your E will be equal to 0. Likewise, your I also will be equal to 0, as omega t is equal to 0, whole thing will be equal to 0. So both E and I will be here at the origin. Now when you apply those values of the angles, when omega t is equal to what, this pi by 2 90 degree, that means when omega t, which is equal to the angle theta, if theta is equal to pi by 2 90 degree, then we know that sine of 90 degree is equal to 1. So it will have instantaneous EMF and instantaneous current as what, E naught and I naught. So what happened at this omega t equal to pi by 2, both E and I will have its peak value or maximum value, I naught for AC current and E naught for instantaneous what, EMF, that will have the maximum value here. So that is depicted or shown here with E naught and I naught here. So what happened when omega t, that means theta is equal to pi 180 degree, I mean at that time what happened, this sine of 180 degree is equal to 0. So sine of 180 degree equal to 0 means what, both E and I will have the 0 value, so it will come in here. Likewise, when you have that omega t theta is equal to 270 degree, or you can have thrice pi by 2, then what happened, it will have what, -1. So it will have the instantaneous EMF and instantaneous current as minus E naught I equal to minus I naught, like that. So it will have in the opposite direction of that one. So we call it this as positive half, and the downward side from this x-axis we call it as what, the negative half. So on the negative half side, what happened, the value of this E and I will be having minus what, I naught and minus E naught. That will be shown somewhere here. It will be minus E naught somewhere here, and corresponding to this it will be minus I naught somewhere here. Okay, so what happened when omega t comes to that of twice pi, that means 360 degree. When omega t comes to that of twice pi or 360 degree, we know that sine of 360 or twice pi will be equal to again 0. Similarly, what happened, E and I will have both 0 value. So that means it will come here again. So when you plot that graph, then it will be just like this. Okay, of the shape of this. So we call this type of shape of graph as sinusoidal graph, or for the sinusoidal function it will be having this sine graph. Got it? And see, in the case of sine graph, it started from the origin. When t is equal to 0, it starts from the origin, and it gives you one form of complete wave, as you have learned in class 11, okay, in simple harmonic motion. So this will give you one complete wave. That means first half, second half. First half we take it as a positive half, and the second half as negative half. Why? Because it is negative in the downward direction of this reference time axis, or angle theta axis. Okay, now if you try to take it in terms of t, if this is having the complete what cycle, then the time taken from the very beginning origin up to here, it is for one complete oscillation. Then it will be having the time what we call as time period capital T. Now if you divided this time into 4 equal parts, then this will be t by 4. So at t is equal to t by 4, what happened, this omega t, it will be omega t by 4, nothing but, when if you describe it in terms of angle, then it will be pi by 2. So you can draw in terms of the time or in terms of the angle. Okay, so at t by 4, what happened, your E and I will have their maximum values. When t is equal to capital T by 2, that means half of the time period, then what happen, E and I will have 0 value. When small t is equal to thrice capital T by 4, that means 3 times of quarter of a time period, then what happen, it will have the negative of its peak value, that means E will be equal to minus E naught, I will be equal to minus I naught here at this point when small t is equal to 3 times the quarter of time period. Okay, then what happen when small t is equal to capital T, the time period of oscillation, then what happen, your E and I will have 0 value. So if you keep on continuing, then it will again repeat the same cycle again repeatedly. Okay, so this is the sine function to represent AC EMF or AC current. Now what are these? As I told you that E and I are nothing but these are the instantaneous value of EMF and current, and E naught and I naught, these are peak or maximum value or amplitude of EMF and current. You can call it this as amplitude as it is in the form of wave. Okay, so this amplitude is nothing but we said that it is the maximum displacement at a time somewhere here, that the displacement or the magnitude of current at this time, I mean the instantaneous current, will be up to this point, but EMF will be coming from here up to this blue mark. Okay, at somewhere here the instantaneous magnitude of the current will be coming up to here, but that of the EMF will be little bit more than this, it will be coming up to here like this. So the maximum displacement, okay, of any displacement of any particle, we call it that as amplitude. Likewise here also in the AC current, the maximum value of the current and the maximum value of the EMF, we call it that as either amplitude or peak, or simply just as maximum value of AC current and maximum value of EMF, like that. Okay, where omega, we call it this as angular frequency, or it may be called as angular velocity also, no doubt. T is the instantaneous time, that means the moment that we are taking, the particular time, we call it that as instantaneous time. And omega t, the whole this omega times t, we call it this as phase. Okay, this is very important. Okay, omega t is known as phase. Got it? Now see here, in the case of sinusoidal functions, both omega t in the EMF also and in current also omega t. So if there is no difference in this phase, then we say that they are in phase. AC EMF and AC current, we say these two physical quantity, EMF and current, as they are in phase. Got it? But if there is some difference here, then we will say that there is a phase difference of that much angle, if there is a difference anything here. Now the symbol of AC current is denoted by like this, with a circle and with that sinusoidal function, just like the waveform. Okay, that will represent the symbol for AC EMF or AC current, or simply you can call it that as AC source. Now in the case of cosine functions, when we say sinusoidal functions, both sine function and cosine functions are collectively called as what? Sinusoidal functions. So the previous one was for a sine function, and let's see whether this cosine function can also represent AC current or not. Now if E is equal to E naught cosine of omega t, I is equal to I naught cosine of omega t, instead of sine omega t in the previous one, we are using cosine. Let's see whether this cos function can represent the sinusoidal form of that of the AC current. That means continuously changing its magnitude and periodically reverses its sign. Let's see whether that definition, the property that contained in the definition, whether that two, what are those two properties? Changing its magnitude continuously and changing or reversing its direction periodically. Let's see. So what happened when omega t, same as that in the previous one, okay, omega t, or it may be time that can be drawn along x-axis, and that EMF and current, instantaneous EMF and instantaneous current will be drawn along y-axis. Okay, now this omega t, when omega t is equal to 0 at t is equal to 0, I mean when omega t is equal to 0, then we know that cosine of 0 degree is 1. So what happened, your instantaneous EMF will be equal to E is equal to E naught only. I will be also equal to I naught. That means at the very beginning, when t is equal to 0, it will have its peak value. For SE current also I naught, for SE EMF also it will be having E naught. But when this omega t, okay, that phase omega t theta is equal to pi by 2, or you can have in terms of a time period as t by 4, that means 1/4 of a time period capital T. So what happened at that time of that quarter of time period t by 4, or omega t equal to pi by 2, we know that cosine of omega t is what, 90 degree, cosine of 90 degree. So cosine of 90 degree is what, 0, or you can call it that as cosine of pi by 2. So what happened at that, this all values will be what, 0, 0. So the right side will be equal to 0, E and I will be equal to 0. So it will come to this point. Now when omega t is equal to that of pi 180 degree, I mean, or in terms of time period, you can take it as half of the time period. That means 2 times of quarter of time period. 2t by 4 will be equal to what, t by 2. So at that time, or at this phase phi, what happened, we know that cosine of 180 degree is -1, or cosine of phi you can say is equal to -1. So it will be having its peak value. E is equal to minus E naught, and I will be equal to minus I naught. That will be coming at this point, minus I naught minus E naught at this. Somewhere here it will be minus E naught, somewhere here it will be what, minus I naught. Got it? And when theta is equal to what, thrice pi by 2, that means 270 degree I mean, and in terms of time you can call it as 3 times of quarter of time period, that means 3t by 4. Then what happened at that time, what happened, cosine of 270 degree is again 0. So your E and I, instantaneous EMF and instantaneous current, will be having again 0 value. That will come here. When omega t, the phase omega t is equal to twice pi, or you can call it as theta equal to 180 degree, or at a time that is equal to the time period capital T, then what happened, this cosine of what, omega t will be equal to what, +1. Cosine of twice pi is equal to cosine of 0 degree. So cosine of 0 degree is 1 again. So what happened, E will be equal to E naught, and I will be equal to what, I naught. That is coming here at this point. Same at the initial state again it comes. And when you keep on increasing just like that, the time or angle, then it will repeat itself as it was before. So it will keep on continuing like that. So what happened, when you try to plot that graph, then it will be coming in the shape like this for the AC current with the blue with the green color, and for that of AC EMF it will be coming like this in the shape of this graph in shown with the blue color. Okay, so that means in this case also, if you try to shift this what y-axis somewhere here, then it will be just like that of sinusoidal function here like this, or you can move down up to somewhere here so that it will come down again here. Then it will be just like that of what, your sinusoidal function. In the case of sinusoidal function, what happened, the graph starts from somewhere here. This will be your y-axis, and it starts like this in this shape. Got it? So at every point, what happened, the displacement of this current are all different, and it will be maximum somewhere here like that. So maximum, when current is maximum, what happened, your EMF will be also maximum. So they are in phase, we say like that. Got it? So now what happened, from these two that means cosine function and sine function both can represent the AC current and AC EMF. Got it? Now let's see what is meant by average or mean value of AC current. We sometimes call it this as average value or mean value of AC current. What is meant by this average or mean value of AC current? Mean or average value of AC current over a half cycle. Why we are trying to define this over a half cycle? Because if you try to take it the average of that AC current, one coming from the positive half, another coming with the equal amount onto the negative side, if you take the average of it, then it will come to 0. So we never define this average or mean value over a complete cycle. Rather, we will try to define this for a half cycle only. Either it may be positive half or negative half. Okay, so average or mean value of alternating current over half cycle is that steady current. Steady current means DC current. Okay, you can take it. Steady current which will send the same amount of charge in a circuit in the time of half cycle as is sent by the given alternating current in the same circuit in the same time. So let's try to understand this definition. Okay, first, now suppose you are having a circuit somewhere here like this. So let's take it that this is a circuit, and if this is the AC source, okay, that will send current through it. Now let's take it that during a time interval, so let's take it a time interval small t. During this small time, okay, for a half cycle, let's take it the positive half. For a half cycle, if AC current is passing through it, and let's take it that the amount of charge that is transferred through this circuit, let's take it as Q. So your AC current send Q amount of charge, okay, through this circuit during this interval of time small t. Now we will have to define the mean or average value of AC as what? As that steady current which will send the same amount of charge when this AC is replaced by DC. Okay, when this is replaced by DC, then this circuit will be what? It will be just like that as shown in the cell like this. So what happened when AC current is passed? When AC current is the source through this circuit, Q amount of charge is transferred to the circuit or flowing through the circuit during this small time t. So in the same time small t, if this steady current could pass the same amount of charge in the same circuit during the same interval of time, then this DC or steady current is defined as the mean or average value of that AC current during this half time, okay, during this half cycle of the AC. Got it? Yes, let's try to check it, the formula and all for this. Okay, now I'm repeating again the definition. Average or mean value of alternating current over half cycle is that steady current, means that DC current, which will send the same amount of charge in a circuit in the time of half cycle as is sent by the given alternating current in the same circuit in the same time. Got it? Now if this dq is the small amount of charge that is transferred into that circuit by the AC current, then your dq will be equal to what? I into dt. Why? Because current, we define current as rate of flow of charge, so I will be equal to dq by dt. So your dq will be equal to what? I into dt, right? But we know that instantaneous current I is expressed as I naught sine of omega t, right? So that is what I am writing here. Your dq will be equal to what? I naught sine omega t. So if you want to find out the total charge that is transferred or that is flowing through that half cycle, then in a time period of 0 to t by 2, that means half of the time period, we need to integrate this dq so as to obtain that total amount of charge that is transferred or sent during that half cycle. So how it will be done? So q will be equal to what? Your integration of what? I naught sine of omega t. Your q is equal to integration of dq, that will be equal to q. So integration of this I naught sine omega t from 0 to t by 2. Why? Because t is nothing but this is the time period, okay, of that AC. So if you are going to take it for a half cycle only, then you have to take half of the time period, that is 0 to t by 2. So when you integrate this, what happens? You will get like this. Okay, so how this integration is coming, do you want to see? Okay, let me do it. Okay, now let's take it a blank one. Okay, so your q is nothing but your q, this is equal to nothing but this is dq. So it will be equal to integration of what? I naught sine of omega t dt, and the integrating limits are from 0 to what? T by 2. Got it? This is t by 2, right? Now this peak or maximum value is always constant, so you take it this constant outside the integration, and then it will be I naught, and it will be having integration of sine of omega t dt from 0 to t by 2, like this. Got it? Now then this will be integration of what? I naught, like this, and it will be integration of sine is how much? Minus cosine of omega t, right? So minus cosine of omega t, and that is for integration of this sine function, you need to integrate again the angle again. So integration of omega t will be what? Omega, and the integrating limits are from 0 to what? T by 2, like that. Got it? So it will be equal to what? I naught, you can take it out, that minus along with that omega, because these are all constant, and you need to what? Put the limits for this small t by the upper limit first, and then by the lower limit again. So inside the bracket you will have what? Cosine of what? Omega t by 2 minus cosine of, if you replace it t with this t here with the 0, then cosine of omega t, that means cosine of 0, like this. So what happened? Cosine of omega t, you know that omega, it is nothing but this will be equal to twice pi by t. Got it? So omega t will be equal to what? Twice pi. So cosine of twice pi is how much? Cosine of twice pi divided by 2. 1 2 is there. So cosine of twice pi divided by 2, it will be coming like this. Cosine of twice pi divided by 2, then 2 cancel, then it will be just like cosine of what? Cosine of pi only. Cosine of pi is how much? Cosine of 180 degree is minus 1, right? So let's put it that minus 1. So this will be equal to minus I naught divided by omega. Cosine of omega t by 2 is nothing but this is cosine of pi. So cosine of pi is minus 1. Cosine of 0 is again minus. This cosine of 0 is 1, so we will put it like this. So it will be equal to, within the bracket it will become minus 2. With that minus and this minus, it will be positive. So it will be what? I naught twice I naught divided by omega is coming, right? So what happened? This omega, as I said, it will be equal to what? Twice pi divided by t. So if you put it that value, then it will be again equal to twice I naught divided by twice pi, okay, into t, like this. Got it? Into t, right? So your q will be equal to what? Q will be equal to, after cancelling this, it will be equal to what? I naught T by pi, right? So your Q will be equal to what? Twice I naught T. Oh, 2 has been cancelled. Okay, so there will not be no 2. So I naught T by pi, like this, right? Again, when that what mean or value, mean or average value of AC is passed, that means if a steady current is passed, that means if your steady current is denoted by I mean or I average, if it is passing for a time of T by 2, then the amount of charge that will be flowing will be equal to like this. Q is equal to what? The current times the time. Why? Because current is defined as rate of flow of charge, right? So if this I is your I average or I mean, and Q, this time will be what? T by 2. Then if you try to cross multiply these two, then your Q will be equal to like this, right? So if you equate these two, this is also the amount of charge that is flowing when AC current is passed through the circuit for a time of T by 2, and this is the amount of charge that will be flowing when your steady current is passing through it. So both are of same charge as by definition. So when you equate these two, then your I mean or I average will be equal to what? Let's try to have it like this. T by 2 here, this is this one. Okay, you need to equate it with this one, right? So I naught T divided by pi. Got it? Now what happened when you cancel this TT, then your I mean will be equal to what? Twice I naught by pi. Okay, when you simplify this, then you will get it this as around 0.637 times of I naught. Got it? So we also express this as what in terms of I mean or I average as 0.637 times of I naught, or you can also express this as 63.7% of I naught. Got it? Of I naught, like this. Clear? So that is how we need to what? Derive it, the expression or formula for mean or average value of AC in terms of its peak value. Got it? Now let's see again. So as I have given you the expression that Q is equal to I naught T by pi. That is the first equation. So when AC current is when steady current or DC current is passed through the circuit for the same time of half time period, okay, then the amount of charge will be given by what? IM is equal to what? Q divided by T by 2. Okay, that means your mean or average value will be equal to this. So when you try to express it by equating these two equations, the first one with this Q and this Q that is coming from here, okay, then you will find that your mean or average value, or rather you can put it this expression of Q here also, and after cancelling, that means after simplifying, then you will get it that I mean or average will be equal to like this. That is what I have done. Okay, right? So mean or average value of alternating EMF can be done similarly in the same way as we did in the case of AC current. You can do it for AC EMF also. Same thing, it will be coming that your E average or E mean will be coming up as 0.637 times E naught, or you can call it in terms of what your percentage. That means E will be equal to 63.7 times of that of E naught. Okay, not. Now average or mean value of alternating current or EMF is 0 over a complete cycle. That is why we have taken as what, positive half or either negative half only. Why? Because that much amount of positive half there, that much it will be there in the negative half, but the thing is that only they are in opposite in direction, opposite in sign we can say, so they will cancel each other if we take it for the whole complete cycle. Okay, that is why your mean or average value is generally defined in terms of over this half cycle only. Got it? Yes. Now let's see about the RMS value, root mean square value of AC. We also call it this as virtual value or effective value. Now in this case of root mean square value, what happened, we will take it what any time duration, whether it can be taken as half time period of AC or full complete time period of AC, it doesn't matter, because this is what root mean square, and this root mean square because what your current is going to take as the square. Why? Because we are going to define it in terms of amount of heat produced. Okay, that is why in any heat we know that in Joule's heating effect, H is directly proportional to the square of the current. So if you take the square of negative quantity, then it will be also a positive quantity. So it is immaterial whether it is taken for the half cycle, for a negative half cycle, or for both. Okay, for a complete time period, doesn't matter. So let's try to define it. This root mean square value or virtual value or effective value of AC is that current, okay, which produce the same heat in a given resistance in a given time as is produced by the alternating current in the same resistance in the same time. Suppose if you are having a circuit, okay, having resistance, you are having a circuit having a resistance. So let's take it that this is your AC source, okay, AC source, and this is a resistance. And in this circuit, suppose if you are going to send the amount of AC current for a time, let's take it as T. Time of flow of current is taken as the time period of AC. Okay, let's take it, you can take it T by 2 also, doesn't matter. Okay, or even T by 4 you can also take it, so anytime. So let's take it that the time of flow of AC current, okay, through this circuit having resistance R, let's take it as capital T. So during this time capital T, what happened, let's take that the amount of heat, okay, generated or produced or developed through this resistance, let's take it that as H. Okay, when this resistance, okay, when this circuit, if the source of EMF is replaced by a steady source, okay, we generally take it that steady source as the DC source. So during this same time capital T in the same circuit, okay, if the amount of heat produced is also same when this steady source or steady current is passing through the circuit for the same time, and if this Q amount of heat, okay, if these are same, then that current, that steady current which flows, okay, through the same circuit during the same time, and if it is produced the same amount of heat, then that steady current we call it as what, the RMS value of this AC. Okay, that steady current we call it that as RMS value or effective value or virtual value of the AC. So we will call it that virtual value as denoted by what, IV in the case of AC current or EV in the case of AC EMF. So these IV, what is, we call it as alternating current, that means virtual value of effective virtual value or effective value of the AC is defined as the amount of current which will what, generate the same amount of heat as is produced by the AC when what, DC current is passed through the same circuit, okay, having the same resistance during the same time. Got it? That value of the steady current we call it as what, RMS value or steady RMS value or effective value or virtual value. Got it? Yes, let's try to express it those things as we have done in the case of what your mean or average value. Let DH be the small amount of current that is generated or produced in that circuit having resistance when AC current I, okay, instantaneous AC current I is flowing for a small time dt. Then we know that dH will be equal to I square R dt. From where it is coming? It is coming from that Joule's heating effect. H is equal to I square RT. Okay, so I, you try to express it in terms of that sinusoidal function. I is equal to I naught square R sine square omega t dt. Okay, then if you want to find out the total amount of heat produced during the whole cycle or whole cycle of the AC, then you need to integrate this dH, so that it will be what? Integration of H will be equal to integration of what? I naught square R sine square omega t dt from 0 to t. Now this will be equal to I naught square RT divided by 2, where omega is nothing but this is the angular frequency, and it can be replaced by what? Twice pi by t. And you know how it is coming, this formula. If you want to know it, then I will do it. Okay, let's take it as a blank, right? Now your heights, your heights will be equal to what? Integration of what? I naught square R sine square omega t dt, and the integrating limit is from 0 to t. You can also see, you can also do by yourself by changing this integrating limit from 0 to t by 2 also. It will come the same result. Okay, now we know that there is no definite formula for integration of sine square, right? So we need to express this sine square in terms of that of cosine. We know that sine square theta, this is equal to what? 1 minus cosine of twice theta divided by 2, right? So we'll need to express this in terms, this sine square in terms of cosine function, so as to integrate. Okay, we are going to change, okay, to an integrable function. Okay, so if we change that one, then it will be having what? This will be equal to integration of, so you can take it out, this I naught. Okay, I naught and R outside the integration, because these are what? The constants. Peak value, then resistance, these are constants, so you can take outside the integration, and the integrand that is having is what? Instead of sine square, we are having 1 minus cosine of twice theta divided by 2, no? Divided by 2. That 2, that can be also taken outside, and whatever it is having is what? This much only. Clear? Like this. So if you try to integrate it, then you need to integrate it separately. There are two terms. One into dt will be dt, so integration of dt minus integration of cosine of this twice omega t. I'm sorry, instead of this theta, it will be now as omega t. Okay, so cosine 1 minus cosine of twice omega t, okay, dt. From where it is changing? It is changing due to this relation. Okay, now this will be equal to what? I naught square R divided by 2. Now let me put like this. Integration of dt will be t only, and the limits will be from 0 to t, minus cosine of twice omega t. We know that integration of cosine of omega t, it is nothing but it will be sine omega t. Cosine of omega t means sine of omega t. So what happened? Your integration for cosine minus sine is for this minus. Okay, cosine of omega t means what? Sine of twice omega t, and this is for the integration of sine of twice omega t. Now we need to again integrate the angle. If you integrate this twice omega t again, then you will get it as twice omega, and the limits are from 0 to t, like this. Got it? Yes. So what happened? This will be equal to I naught square R divided by 2, and this, if you replace the variable by the upper limit, okay, if you replace this t by the upper limit minus replaced by the lower limit, that means t, capital T minus 0. So that capital T will be placed here, minus 0 is immaterial, so I will not put it. So if you do this, okay, by replacing that capital T to this small t, and if you do the simplification, then this will come to 0. So I will not put it this expression, the last expression. So whatever you have is only this, the first term. Got it? So you will have what? It will be having what? This will be having I naught square, okay, I naught square RT divided by 2. Got it? So after cancelling all these things, let's see again. Just remember that h is equal to I naught square RT by 2. That is what h is equal to. Let me put it that h is equal to I naught square RT divided by 2. Was it this? Yes, no? So what happened when this mean, not mean, your RMS value or AC current, RMS value or effective value or virtual value of AC current is passed through that circuit having resistance for this time t, then that amount of heat produced will be again equal to what? It will be I virtual is nothing but your RMS value or effective value, okay, this square into R into T, okay, this will be the amount of heat produced by the steady current. That steady current we call it as mean or average value, okay, of AC. So this heat, okay, produced from the steady current and this heat produced from the AC source, as per definition they are of the same. So if we equate these two, then it will be coming as IV square RT, this is capital RT, this will be equal to I naught square RT divided by 2, like this, right? So if you cancel this R with T like this, then your IV square will be equal to I naught square divided by 2. So if you try to express this IV, then it will be equal to what? I naught divided by root 2. Got it? So if you try to multiply, if you try to simplify this, then your IV will be equal to what? Your IV will be equal to 0.707 times of I naught. So this is an expression, okay, relating between what your virtual value and the peak value. Similarly for EMF also, EV can be expressed as 0.707 times of what? I naught. Or you can express this in terms of percentage as what? 70.7% of what? I naught, like that. Similarly for EMF also, EV can be expressed as 70.7% of what? E naught, like that. Got it? So let's see the slide. Let's go to the slide again and we will see what is having there. Okay, now let's see, whatever we have done, it will be coming up again here. So if IV is the virtual value of AC, then what happened? H can be expressed as IV square RT. So if you equate these two, then what happened? You will get it, the expression that I have shown you, that IV or IRMS or I effective, okay, this has the same meaning. These are all RMS value, and this will be equal to I naught by root 2. When you simplify it, then you will get it as 0.707, okay, times of I naught, that is equal to like this. Okay, now you can express it similarly in the case of AC current like this. You can do for EMF also, same thing. Okay, Now root mean square value, as I said, okay, it can be calculated for over any period of time, whether it may be for one complete cycle, half cycle, quarter cycle, doesn't matter, okay. But you need to remember that you should not use this formula if the time interval under consideration is less than one period. If you are using this, then what happen, it will be different, okay, because as we are having only time period t here, we take it the formula like this, t here like this. Got it? If it is of a half time period, then this will be only coming up like this, and it will be t by 2 here. Got it? So it will be different, right? But you can try it for any period of time, whether it may be t by 4 here. If you are going to t by 4, then you need to replace it this formula by simplification, okay, and the time here will be again iv square r t by 4. You need to take it like that, and if you equate it, then the formula will be coming as like this, the same thing. Got it? Yes. Now let's see what is the relation between this peak value, okay, virtual value and mean value. The relative values of this peak value, the maximum, I mean the virtual, or we call it that as RMS value, and the mean value, we call it that mean value as average value, okay. So what is the relation lying in between this what peak value, virtual value and average value? We know that mean value or average value is equal to 63.7% of E naught, or in terms of decimal you can write it 0.637 times of E naught. Virtual or effective value is equal to 0.707 E naught, right? So if you try to draw the graph, then it will be seen as like this. Got it? Your E naught is peak, it is the highest, and E virtual will be little bit less than it because it is 70.7, and your mean value is again little bit smaller because it is 63.7 only, right? So 63.7% of this peak value. Got it? So like that you will see the mean or average value, virtual or RMS value, and a peak value like this. Got it? So let's see some tips or some notes to be taken. The given value of alternating EMF and current are virtual value unless otherwise specified. Okay, if it is not stating that this is your mean value or average value, otherwise we have to take it that as RMS value, what we call as virtual value. That is what, let's take it like, for example, that 230 volt AC means what? That is your mean, that is not mean, rather that is your virtual or RMS value, or you can call it that as effective value. But if it is going to mean your mean or average, then it will be specified that as 230 volt. Okay, if it is going to 230 volt, they are going to express it, then they have to state it that this is the mean value, or if what your average value of AC is 230 volt, like that. If it is not specified, then we have to be understood that that is nothing but that given voltage or potential difference is what RMS value or effective value, or we can also call it as virtual value. So your effective value is what? 230 volt. AC meter, okay, AC ammeter and AC voltmeter read the RMS value of alternating current and voltage respectively. So in the case of AC ammeter and voltmeter, what happened? Whatever the AC ammeter and AC voltmeter that read, okay, the value is nothing but that is of the RMS value only. They are called as hot wire meter. Why? Because they are going to measure the amount of heat produced only. Okay, indirectly they are going to indicate what the voltage or the current, but they are trying to measure it indirectly there inside it as the amount of heat produced. That means that is heat produced is for what? For a RMS value. Okay, so they are called as hot wire meter. The scale of DC meter is linearly graduated, whereas that the scale of the AC meter is not evenly graduated because of that Joule's heating effect. Heights, okay, heat is directly proportional to the square of the current. So in the case of hot meter or AC meter, Okay, SE emitter and SE voltmeter, the scales are not graduated uniformly, rather not evenly we can say, because why? The amount of heat is directly proportional to the square of the current. Okay, as current is little bit changed, then what happen? The amount of heat developed will be what in terms of square of that change in current. Got it? So with that, we will come to the end of our today's topic. Thank you very much for listening or for viewing my video.